Hello. I'm going to go through the OCR 2022, A-Level, Chemistry, Paper 2, Synthesis and Analytical Techniques. If you found this video useful, please click like, and leave a comment, as it will help to carry on making more videos like this. In the fixed comment under the video, I leave a link to my website jctnotes.com where you can see the written answers to this paper. I also leave a link to the OCR reaction pathways, that will help you in the preparation for the exam. We start with section A. In question 1, we are asked, which statement is correct for the different rates of hydrolysis of chloride and bromides compounds? A. Bromide compound is hydrolysed faster because chloride is more electronegative than bromide. B. Bromide compound is hydrolysed faster because the carbon-chloride bond enthalpy is greater than carbon-bromide. C. Chloride compound is hydrolysed faster because chloride is more electronegative than bromide. D. Chloride compound is hydrolysed faster because the carbon-bromide bond enthalpy is greater than carbon-chloride. As the question is asking about hydrolysis of compounds of chloride and bromide, I assume that R is an alkyl group and we are asked about halogenoalkanes. The hydrolysis of halogenoalkanes follow the reaction. In the haloalkanes, the greater the atomic number of the alkane, the more reactive the haloalkane is, therefore we know that the bromide compound is going to be hydrolysed faster, answers A and B. We need to decide if it is due to the electronegativity or the bond enthalpy. The hydrolysis of haloalkanes is a nucleophilic substitution, where the carbon-halogen bond is broken and the carbon-oxygen is formed. As a bond needs to be broken, the bond enthalpy is more relevant than the electronegativity on this question, therefore the answer is B. In question 2, we are asked which statement about absorption of radiation is correct? A. Infrared radiation can result in the breakdown of the ozone layer. B. Ultraviolet radiation can cause some polymers to photodegrade to benefit the environment. C. Ultraviolet radiation is linked to global warming. D. Ultraviolet radiation is used in modern breathalysers to measure ethanol in the breath. A. Is not true as the breakdown of the ozone layer is due to the ultraviolet, not infrared radiation. B. Is true. C. Ultraviolet radiation is not directly linked to global warming. Global warming is more related to absorption of infrared radiation by greenhouse gases. D. Breathalysers work by the reaction of alcohol with potassium dichromate that is converted to electrical current. Ultraviolet radiation is not used on these devices. The answer is B. In question 3 we are asked what is the number of sigma bonds in a molecule of methylbenzene? 7, 10, 12, or 15. If we count the single bonds between the carbon-carbon, one for each double carbon-carbon bond, only one of them is sigma bond, the other is a pi bond, and for each carbon-hydrogen, we have 15. The answer is D. In question 4, we are asked which functional groups are present in a given structure. A. Amide and alcohol. B. Amide and carboxylic acid. C. Amine and carboxylic acid. D. Amine, ketone, and alcohol. We can identify an amide group, an alcohol group. Therefore, the answer is A. In question 5, we are asked how many chiral carbon atoms are there in a given structure. 5, 6, 7, or 8. A chiral carbon is a carbon with 4 different groups attached. We need to be careful that we are considering the whole group attached, not only the next atom. Counting the number of chiral carbons, I get 8, and the answer is D. In question 6, we are given 4 processes to prepare ethene. We are asked which process has the highest atom economy, assuming that ethene is the only product that is used. We define the atom economy as the molecular mass of ethene divided by the molecular mass of reactants and multiplied by 100. We need to bear in mind that in reaction A, we produce 3 mole of ethene, in reaction B, 2 mole, and in reaction C and D, 1 mole. The molecular mass of ethene is 28 grams per mole. And we can calculate that the atom recovery for A is 59.15%, for B is 65.12%, C is 43.41% and D is 60.86%. The highest number is 65.12% for reaction B. The answer is B. In question 7, we have that the complete combustion of 0.05 mole of an alkane produces 5.4 grams of water. We need to identify the molecular formula of the alkane from the 4 molecules provided. The complete combustion of an alkane with water produces water and carbon dioxide. In this exercise, we only need to focus in the alkane and the water. For 1 mole of alkane we are going to obtain 3 mole of water in alkane A, 4 mole of water in alkane B, 5 mole of water in alkane C and 6 mole of water in alkane D. As the molecular mass of water is 18 grams per mole, we can find that 5.4 grams is 0.3 mole of water. These 0.3 mole of water have been provided by 0.05 mole of alkane. If instead of 0.05 mole of alkane, we had 1, we would have obtained 6 mole or water. This proportion of alkane and water only appears in option D. The answer is D. In question 8, we are given the structure of the paracetamol. A tablet contains 3.31 by 10 to the power of minus 3 mole of paracetamol. We are asked what is the mass of paracetamol in the tablet. The formula of the paracetamol can be written as C8H9O2N, with a molecular mass of 151 grams per mole. With the molecular mass, we can find that 3.31 by 10 to the power of minus 3 mole of paracetamol is 500 milligrams. The answer is C. In question 9, we are given a compound that reacts with hydrogen gas to form a saturated compound. We are asked which of the given volumes of hydrogen, measured at room temperature and pressure, reacts with 0.05 mole of the compound. I redraw the structure to make it clearer. When we fully saturated the compound, we have added 8 atoms of hydrogen. As the hydrogen is a diatomic molecule, we need 4 molecules of molecular hydrogen that will react with 1 mole of compound. As we have 0.05 mole of the compound, we are going to need 0.2 mole of hydrogen. Using the ideal gas equation, we know that 1 mole of hydrogen at room temperature and pressure occupy 24 cubic decimeters, consequently, 0.2 mole of hydrogen occupy 4.8 cubic decimeters. The answer is C. In question 10, we are asked which compound, from the 4 given, is one of the product of the hydrolysis of butyl propanoate by aqueous sodium hydroxide. Butyl propanoate is an ester. Ester can be hydrolysed in alkali and acidic conditions. In acidic conditions, the ester reverts to the original alcohol and carboxylic acid that forms the ester. In case of alkali conditions, the salt of the carboxylic acid, carboxylate, and the alcohol are formed. In this case, hydrolysation of butyl propanoate with aqueous sodium hydroxide will form the sodium propanoate and the butanol. Sodium propanoate is the second option given. The answer is B. In question 11, we are given an infrared spectrum of an organic compound. We are asked to identify the compound that could have produced the spectrum from the 4 options given. Looking at the spectrum and the data sheet from the exam, we can identify the following peaks. A peak between 2800 and 3100 reciprocal centimeters, indicating a possible alkyl group. Another peak at around 1750 reciprocal centimeters, in the region of the carbon-oxygen double bond. Anything below 1500 reciprocal centimeters is considered fingerprints and we can ignore it. We start by checking compounds A. It has a double bond that give a peak between 1620 and 1680 reciprocal centimeters, but this peak is not shown in the given spectrum. Option A is discarded. We move to option B. We can see two alkyl groups and a carbon-oxygen with double bond, as in the spectrum. Option B fits the profile. We carry on with option C. We can see an amine group, that will give a peak between 3300 to 3500 reciprocal centimeters, but it is not in the spectrum. C can be discarded. Option D also have an amine group, as in option C. For the same reason, this option is discarded. At the end, we are left with option B as the correct answer. In question 12, we are asked which of the four given compounds will show two triplet in the proton NMR spectrum. We are going to see a triplet when a carbon-hydrogen bond is adjacent to a carbon with two hydrogens. To obtain two triplets, we need that each adjacent group has different environment. Let's see case by case. Option A has two possible triplets, as we have two methyl groups linked to a carbon with two hydrogens each, and these triplets will be different as one of the adjacent carbons is attached to another carbon and the other adjacent atom is attached to an oxygen. A is a possible answer. In option B, we have two methyl groups linked to a carbon with two hydrogens each. However, due to the symmetry of the molecule, these adjacent carbons are similar and both peaks appear as one, not two. B is not the answer. In option C, due to the symmetry of the molecule, we are not going to have two triplets, therefore C is not the answer. In option D, we have also the same case than in C. Then, D is not the answer. The only option left is A. A is the answer. In question 13, we are provided with three equations for a radical substitution. We are asked to identify which equation, or equations, could be part of the propagation step. In equation 1, we are forming the chlorine radical. This radical is able to continue the propagation by forming other radicals. Equation 1 is a possible propagation step. In equation 2, we are forming a radical hydrogen. The chloride radical will form hydrochloric acid before producing an hydrogen radical, as the hydrogen radical is highly reactive. Equation 2 is not a possible propagation step. In equation 3, we are consuming radicals and not producing. This is a termination step. Only equation 1 can be considered a propagation step. The answer is D. In question 14, we are provided with three species and asked which species could react as a nucleophile. A nucleophile is a chemical species that forms bonds by donating an electron pair. All the species given have electrons pairs to donate. So, the answer is A. In question 15, we are asked which isomer or isomers of the three given isomers have four peaks in their carbon-13 NMR spectrum. Peaks are produced by non-equivalent atoms of carbon. In the first isomer, 3-methylbutane-2-OL, we have four non-equivalent atoms of carbon. This is one of the isomers. In the second isomer, 2-methylbutane-2-OL has also four non-equivalent atoms of carbon. This is a second isomer. In the third isomer, 2-methylbutane-1-OL, all the five carbon atoms are not equivalent. This isomer produces 5 peaks. Only 1 and 2 produce 4 peaks. The answer is B. We start with section B. Question 16 is about unsaturated hydrocarbons. In part A, we are given an unsaturated hydrocarbon A. The first question is to give the systematic name of the hydrocarbon A. We have that the longest chain with the double bond has 6 carbons, it is going to be hex. We start numbering in such a way that the double bond has the lowest number possible. We have a double bond in carbon 2, that makes it hex 2n. We have a methyl group in carbon 3. That makes it 3-methyl. Therefore, the systematic name is 3-methyl-hex-2-ene. The second question is to outline the mechanism for the reaction of hydrocarbon A with bromine, including curly arrows and relevant dipoles. First, as the bromine molecule approaches the double bond, the pi electrons in the double bond induce a dipole on the bromine molecule. Then, a bond is formed between the carbon and the bromine, forming a positively charged species called a carbocation. Finally, the carbocation is attacked rapidly by the remaining bromine ion to form the dibromide. In question 16, part B, we have 2 compounds, B and C, that are branched hydrocarbons that are structural isomers of C6H12. Compounds B and C both have stereoisomers. Compound B has cis and trans isomers but does not have optical isomers. Compound C has optical isomers but does not have cis and trans isomers. We have 4 questions on this section. The first question is to define the term structural isomers. Structural isomers are compounds with the same molecular formula but different structural formulae. The second question is to define the term stereoisomers. Stereoisomers are compounds whose molecules have the same atoms bonded to each other but with different arrangements of the atoms in space. In the third question of question 16, part B, we are asked to draw the structures for the cis and trans isomers of the branched hydrocarbon B. I make space for this question. C6H12 indicates that is an alkene, general formula CnH2n, we know that it is branched with isomers cis, the same groups are on the same side of the double bond, and trans, the same groups are on opposite sides of the double bond. There is not a unique answer and you might come with another valid response. I develop my own here in case you need some help. I start by drawing the double bond. I have used 2 atoms of carbon, I have 4 atoms of carbon more to be filled. Several options. First, use 4 methyl groups, CH3, but these will not give cis-trans isomers. Discarded. Second, use 1 ethyl group, CH2CH3, and 2 methyl groups, CH3, this could work. Third, use 2 ethyl groups CH2CH3, this could also work. In the fourth question of question 16, part B, we are asked to draw the structures for optical isomers of the branched hydrocarbon C. I make space for this question. We know that it is branched, and being an optical isomer means that it is going to have an atom carbon with 4 different substituents. This carbon with 4 substituents cannot be an end carbon, as it will be methyl group CH3 and therefore, it will have 3 substituents as hydrogen. Let's say that we made R1 equals to hydrogen, we made R2 equals to methyl group CH3. We have 4 atoms of carbon to replace R3 and R4, none of them can be as CH3, as we already have this group, so the only option left is to use 2 chains carbon-carbon, one with a single bond and the other with a double bond. This leads to. We can draw the specular image of this compound. I copy here the answer from the marking scheme, that it is nittier than my drawing. In the fifth question of question 16, part B, we have compounds D and E, that are 2 more structural isomers of C6H12. Compounds D and E do not show stereoisomerism. We are provided with NMR and infrared, IR, spectral data for D and E. We are asked to draw the structures of D and E and explain how the spectral data in the table provides evidence for the structures. We start with compound D. One peak in the proton NMR spectrum indicates that all the hydrogen atoms are equivalent. One peak in the carbon NMR indicates that all the carbon atoms are equivalent. No peak between 1620 and 1680 reciprocal centimeters indicates that there is no double bond. This means that all the units are going to be the same. As we have 6 atoms of carbon and 12 atoms of hydrogen, all the structures are CH2. The structure of D is cyclohexane. We focus now in compound E. One peak in the proton NMR spectrum indicates that all the hydrogen atoms are equivalent. 2 peaks in the carbon NMR indicates that there are 2 types of carbon atoms. A peak between 1620 and 1680 reciprocal centimeters indicates that there is a double bond. If we start by creating the double bond, we have. The only way that we can have 2 peaks in the 13 carbon NMR is if all the radical groups are the same and they are methyl group CH3. Also, this make of all the hydrogen atoms equivalent and the proton NMR gives 1 peak. Compound E is 2,3-dimethyl but 2-ene. Question 16, Section C, is about ozonolysis, where ozone breaks carbon double bonds to form carbonyl compounds. As example, we have the complete ozonolysis of methyl but 2-ene. In the first question, we are asked to draw the structures of the products expected from the ozonolysis of 2 given compounds. Following the scheme given, we need to replace the double bond by 2 atoms of oxygen, 1 in each atom of carbon. The carbon and the oxygen are linked by a double bond. In the second question, we are given the first step in the ozonolysis of methyl but 2-ene with curly arrows. We are asked to draw the structure or structures for the products of the given step. Curly arrows are used to show the movement of electron pairs. In the given mechanism, the double oxygen-oxygen bond is broken while carbon-oxygen bonds are created. Question 17 is about an analysis of an unknown organic compound X. We are given the molecular formula as CXHYF60. We have the functional groups carbon fluor and carbon oxygen carbon. There is a chiral atom. We are also given the mass and the volume of the compound gas at given pressure and temperature. We are asked to determine the molar mass of the compound X, its molecular formula and draw a possible structure. Using the equation of the ideal gas, we can calculate the number of mole of the compound X. Remember to convert 186 cubic centimeters to 186 by 10 to the power of -6 cubic meters and use the temperature in Kelvin. I get 7.9 by 10 to the power of -3 mole. If we divide the mass by the number of mole, we have the molecular mass as 168 grams per mole. We know that the compound has 6 atoms of fluor and 1 atom of oxygen. The contribution to the molecular mass of the fluor is 6 times 19 equals to 114 grams per mole and the contribution to the molar mass of 1 atom of oxygen is 12 grams per mole. Fluor and oxygen combined have a contribution of 114 plus 12 equals 126 grams per mole. If we subtract this contribution to the molecular mass of the compound, we have that 168 minus 126 equals to 38 grams per mole, that need to be supplied by the carbon and the hydrogen. As we have a carbon-oxygen-carbon as functional group, we have at least 2 atoms of carbon. If we use 2 carbons, their contribution to the molecular mass is 2 times 12 equals to 24 grams per mole, leaving 38 minus 24 equals to 14 grams per mole to be filled by hydrogen. This means 14 atoms of hydrogen and 2 atoms of carbon, a number difficult to combine. A molecular formula C2H14F60 looks very improbable. If we use 3 atoms of carbon, their contribution to the molecular mass is 3 times 12 equals to 36 grams per mole, leaving 38 minus 36 equals to 2 grams per mole to be filled by hydrogen. This means 2 atoms of hydrogen and 3 atoms of carbon. C3H3F6O looks more probable. We know that we have 1 chiral atom of carbon, this means a carbon with 4 different radicals. Let's say that we put R1 as carbon-oxygen-carbon. This leave as 1 atom of carbon, 2 atoms of hydrogen and 6 atoms of fluor to complete R2, R3, and R4. To ensure that we have a chiral center, we replace each of this radical with one of these different atoms. We have ensured that we have a chiral atom and we have left 1 atom of hydrogen and 5 atoms of fluor. We have 2 possible structures, both of them acceptable. I just add the molecular mass and the molecular formula in the answer. Question 18 is about carbonyl compounds. In part A, we have 2 questions. In the first question, we are asked to describe a chemical test to confirm the presence of a carbonyl group and how could the product of this test be used to identify the carbonyl compound. We are not allowed to include spectroscopy. This is a very standard test to identify carbonyl groups, aldehyde and ketones. To obtain the 3 marks, cover the 3 following points. 1 addition of a solution of 2,4-D-NPH will produce an orange precipitate. 2 The precipitate can be purified by recrystallization. 3 Melting point of the crystals obtained can be used to identify the compound by comparing to known values in database. In the second question, we are asked to describe a chemical test that would identify whether a carbonyl compound is an aldehyde, including the reagent and observation. Addition of Toland's reagent, an aqueous solution of silver nitrate in excess ammonia solution, will produce a gray precipitate of silver, or a silver mirror is formed on the test tube. An alternative method accepted in the mark scheme is the addition of acidified dichromate, 6, will be turned green. In part B of question 18, a student is provided with 2 unknown carbonyl compounds, F and G. The compounds are analyzed and found to have identical percentage compositions by mass, details given, and we are also provided with the mass spectra of the 2 compounds. We are asked to identify the structure of both compounds. I will start by making space to identify the empirical formula of both compounds. To calculate the empirical formula, I always create a table with 5 columns. The first column is for the name of the atom. The second column is for the atomic mass. The third column is for the mass of percentage of each atom. In the fourth column I calculate the number of moles by dividing the mass with the atomic mass. In the last column, I divided each number obtained in the previous column by the lowest number obtained in the previous column. The first column and third columns are filled with the data of the problem. The second column is filled with data from the periodic table. The fourth column is the division between the third and the second. In the fourth column, the lowest number is 1.7243. In the fifth column, I divide each number from column 4 by 1.7243. The numbers obtained will give the proportion of atoms in the empirical formula. We get C3H6O. We continue with part B of question 18. We have found that the empirical formula is C3H6O. The empirical formula is equivalent to a molecular mass of 58 grams per mole. Both spectra has a maximum m/z at 58 grams, the peak at 59 is due the carbon-13, therefore we can conclude that the molecular mass is also C3H6O. To solve these type of problems, we need to take the atomic masses of the different elements involved and check the formula masses of the possible groups formed with these elements. I start with the heavy elements, carbon and oxygen in this problem, leaving the hydrogens for fine-tuning. I start with spectrum of compound F. The peaks with greater relative intensity are at m/z equals to 29, 28, and a not small portion to 27. With the aid of the periodic table, can find that 1 atom of carbon and 1 atom of oxygen give a relative mass of 12 plus 16 equals to 28. 2 atoms of carbon give a relative mass of 24. If we use the atoms of hydrogen, we can identify the peaks as, and the structure of F is. We now focus in compound G. It presents the peaks with greater relative intensity at m/z equals to 43 and 15. Using carbons and oxygen, we can find that 2 atoms of carbon and 1 atom of oxygen give a relative mass of 2 times 12 plus 16 equals to 40. The addition of 3 atoms of hydrogen gives a relative mass of 43. We can think that the m/z equals to 43 peak is due to CH3CO. CH3 gives a m/z equals to 15, quite useful to bear in mind when checking mass spectrum. With this information, we can find that the compound G is. In question 18, part C, we have an organic compound H that contains carbon, hydrogen, and oxygen only and has a molecular mass of 114.0. Compound H has 2 carbonyl groups and no other functional groups. We are provided with its proton NMR spectrum, where the numbers by the peaks are the relative peak areas. We are asked to suggest a possible structure for compound H. Show our reasoning. I work with NMR spectrum in 2 stages. First, I identify the possible groups that generate the peaks, and second, I put all the pieces together like in a puzzle until I get the structure that match the data. To identify the peaks, I follow 3 steps in order. First, shift to identify the possible group from the datasheet table. Second, splitting pattern to identify how many hydrogen atoms the adjacent atom has. Third, relative peaks area to identify the number of hydrogens in the same conditions. You can create a table with 3 columns if you want. As I don't have space here for a table, I will not use it. We start with the peak at shift between 1 and 1.2 ppm. First, shift. From the data sheet, this is going to be an hydrogen attached to a carbon link with a single bond to another group. Second, splitting pattern. It is a doublet. This means that the carbon of this hydrogen is going to be attached to a carbon with a single hydrogen. Third, relative peak area. The relative peak area is equals to 6. This means that we have 6 atoms of hydrogen under the same environment. This could mean 2 possible solutions. The first option is 2 group CH3 attached to the carbon B. The second option is 3 group CH2 attached to the carbon B. This option leads to a big structure that is going to be incompatible with the rest of the problem, and I discard the structure now. With a suitable structure identified by the peak at shift around 1 ppm, we move to the peak between 2 and 2.5 ppm. First, shift. From the data sheet, and bearing in mind that we have 2 carbonyl groups, this peak refers to a hydrogen attached to a carbon attached to the carbonyl group. Second, splitting pattern. It is a singlet. This means that the carbon of this hydrogen is going to be attached to a carbon with no hydrogens attached to it. Third, relative peak area is 3. This means that they are going to be atoms of 3 hydrogens under the same environment. He can consider that the structure is going to be H3CCOR. We are left with the peak near to 3 ppm. First, shift. From the data sheet, and bearing in mind that we have 2 carbonyl groups, this peak refers to a hydrogen attached to a carbon attached to the carbonyl group. Second, splitting pattern. It is a septet. This means that the carbon of this hydrogen is going to be attached to atoms of carbon with a total number of 6 hydrogens, like 2 methyl groups. Third, relative peak area equals to 1. This means that this is going a unique hydrogen under the same environment. This is the hydrogen that appears by itself in the shift at 1 to 1.2 ppm. With the peaks identified, we need to fit the pieces together. The first thing that I can think is to replace the R's with the groups available to get. However, there are a couple of things missing on this structure. First, the molecular mass is 86, and not 114. Second, there is only one carbonyl group, not two. The addition of another carbonyl group will solve these problems. Or in a more compact form. Question 19 is about compounds that contain the carboxylic acid functional group. In Part A, we work with reactions of carboxylic acids with alkalis, metals, and carbonates to form salts. We are asked to write full equations for the following three reactions, showing structures for organic compounds. First, the reaction of propanoic acid with aqueous potassium hydroxide. The reaction of acid with alkali produces salt and water. Second, the reaction of aqueous methanoic acid with magnesium. The reaction of acid with metal produces salt and hydrogen. Third, the reaction of the alpha amino acid, aspartic acid with an excess of aqueous sodium carbonate. The reaction of acid with carbonate produces salt and carbon dioxide. In question 19, Part B, we are given the structure of 2-hydroxybutanoic acid and we are asked to fill the flowchart provided. Have a look, in the fixed comment below this video, to the link to the OCR reaction pathways that is very helpful for this type of questions. The formation of carboxylic acids from nitriles is performed in diluted acid and heat. NaBH4, sodium tetrahydroborate, is a typical reducing agent that reduces ketones and aldehydes to alcohols. Looking at the structure of the 2-hydroxybutanoic acid, we can write the reactant as. The last two reactions are esterification of reactions, with the reaction of an acid with alcohol to form ester and water. Starting from the left, we can easily see the bond formed and get as product. And to finish with the right, we can easily identify the bond and write the product as. Part C of question 19, is about polymers derived from carboxylic acid monomers. We have three questions. In the first question, we have that pent-3-enoic acid, is an addition polymer. We are asked to draw the structure of pent-3-enoic acid and two repeat units of this polymer. From the name of acid, pent-3-enoic acid, we know that it is going to be a 5 carbon units, with hydroxylic carbon in the first carbon and a double bond in the third carbon. The rest is going to be filled with hydrogen atoms. We can write the pent-3-enoic acid as. To obtain the two repeat units, we need to remember that the addition takes place in the double bond by breaking two double bonds and generating two single bonds. It helps if you draw the molecule that you can see how the bonds form. We move to the second question to the part C in question 19. We have the butane dicarboxylic acid and 1,4-dihydroxy-2-methylbenzene react to form a condensation polymer. We are asked to draw one repeat unit of this condensation polymer. In this condensation polymer, a carboxylic group is going to react with a hydroxyl group from the alcohol, forming a single bond and producing water. If we draw the molecules, we can see where the bond is going to be formed, and it is easy to draw the repeat unit. In the third question to the part C in question 19, we have repeat units of a condensation polymer. We are asked to draw the structure of the monomer required to form this polymer. We can use reverse engineering and think that this is the opposite reaction that we have seen in the previous question, having the water breaking the bond. In the graph we can see where the breakage occurs. With this information, we can draw the monomer. Part D of question 19 is about a polymer formed from 400 molecules of 2-aminopropanoic acid. In the first question, We are asked to draw one repeat unit of this polymer. The structure of the 2-aminopropanoic acid is. The polymerization occurs due to the condensation between the amino group and the carboxylic group. Therefore, a unit of the polymer is. In the second question, we are asked what is the relative molecular mass of the polymer. The formula of the 2-aminopropionic acid is C3H7O2N, giving a relative molecular mass of 89. The relative molecular mass of 400 molecules is 89 times 400 equals to 35,600. We must account for the loss of 399 molecules of water that we lose in the polymerization of 400 molecules of 2-aminopropanoic acid. With a relative molecular mass of 18, 399 molecules have a relative molecular mass of 7,182. Subtracted to 35,600 gives 28,418. In section E of question 19, a student intends to synthesize compound I. We are given the displayed formula. We are asked to plan a synthesis to prepare 9.36 grams of compound I, starting from 2-chloropropanoic acid. The overall percentage yield of compound I from 2-chloropropanoic acid is 64%. We need to include starting mass of 2-chloropropanoic acid, reagents, conditions, and equations where appropriate. As mentioned before, have a look to the link for the OCR reaction pathways in the fixed description. To find a suitable route for the synthesis of the compound, we start by drawing the products that we have or need and the final product. This helps us to visualize the route. We start with 2-chloropropanoic acid. And the final products is. We can see two changes from the start reagent to the final product. First, the chlorine has been replaced by an amine group. Second, the hydrogen in the carboxyl group has been replaced by an ethyl group. The replacement of chlorine by the amine group is performed by heating the 2-chloropropanoic acid in excess of ammonia in ethanol. The addition of the ethyl group can be done by esterification of the produced obtained with ethanol by heating under reflux in concentrated sulfuric acid, a condensation reaction. The relative molecular mass of the compound I is 117 grams per mole. A mass of 9.36 grams, is 0.08 mole. With a yield of 64%, we need to aim for 0.125 mole of compound I. To prepare 1 mole of compound I, we need 1 mole of 2-chloropropanoic acid. Consequently, we need to use 0.125 mole of 2-chloropropanoic acid. The molar mass of 2-chloropropanoic acid is 108.5 grams per mole, and 0.125 mole is 13.5625 grams of 2-chloropropanoic acid. Question 20 is about the chemistry of aromatic compounds. In section A, we are given the structure of compounds J, K, and L. They are structural isomers. In the first question, we are asked what chemical test or tests could be used to confirm the presence of the phenol group in compounds K and L. There are a few tests that could be used. Some of them are 1. With the use of an indicator, for example, litmus paper, the solution should be acidic. However, it should not react with carbonates. 2. The addition of neutral ferric chloride solution to the phenol solution should develop a violet or purple color. 3. The addition of bromine water should show discoloration of the bromine water and a white precipitate formed. In the second question, a student thought that 13-carbon NMR spectroscopy could be used to distinguish between compounds J, K, and L. We need to explain whether the student is correct. The 13-carbon NMR show peaks in all the non-equivalent carbons of the molecule. Equivalent carbon atoms can be easily identified by the geometry. For example, in compound J, if we put a horizontal line in the middle, we can see that the top and bottom are mirror images, and the atom carbons that appear as images will give the same peak. We can see that compound J will show 6 peaks. Compound K have also symmetry, where the top part and the bottom part are mirror images. Compound K will show 5 peaks. Compound L has no symmetry and all the carbons will show peaks, with a total of 8 peaks. The student is correct. In the third question of part A, of question 20, we have that the compound J is substituted at the 2 and 4 positions by chlorine in the presence of a catalyst. We are asked to outline the mechanism for the 4 substitution of compound J by chlorine in the presence of a catalyst, showing the role of the catalyst. The catalyst, like the aluminium chloride, allows the creation of ion chlorine with a Ch +1 that acts as electrophile, and the catalyst is regenerated by the reaction with protons. The mechanism is 1. Electrophilic attack by the electrophile to the pi bond. 2. Formation of the intermediate. 3. The pair of electrons of the hydrogen-carbon bond is transferred to the benzene ring. In part B, of question 20, we are asked to explain why compounds K and L react with chlorine much more readily than compound J. In bullet points, J and K are phenols and they have a pair of electrons on the oxygen that can partially donate to the pi system. The electron density in the ring increases compared to the benzene. The increase in electron density makes it more susceptible to electrophilic attack. In part C, of question 20, compound J is reacted with acidified potassium dichromate under reflux to form organic product M. We are asked to write an equation for this reaction, using O, between squared brackets, to represent the oxidizing agent and showing the structure of M. Compound J is a primary alcohol that will form a carboxylic under the indicated conditions. In question 20, part D, we have a two-stage synthesis of an amine from compound J. In the first question, we are asked to add the reagents for each stage of the given synthesis. The first step is the nitration of the benzene group performed in concentrated sulfuric acid and concentrated nitric acid under reflux. The alkyl group favors the nitration into the positions 2 and 4. The second step is the reduction of the nitro group to form an amino. This is the typical reaction to obtain phenylamine from nitrobenzene, and it is performed by heating nitrobenzene with tin and concentrated hydrochloric acid. In question 2, we are asked to fill in the equation for the reduction stage of the synthesis. The marking scheme allows to use H with square brackets as the reductant, thus, the equation is straightforward, as we are removing 2 oxygens, that need to be lost as water, we use 2 molecules of water. If we count the hydrogens added on the products, we have 2 from the organic compound and 4 from the water. Therefore, we are going to need 6 hydrogens, that we write as the general form for reductors as H with square brackets. However, if you want to use tin and hydrochloric acid, the procedure is similar, as we are removing 2 oxygens, that need to be lost as water, we use 2 molecules of water. If we count the hydrogens added on the products, we have 2 from the organic compound and 4 from the water. Therefore, we are going to need 6 hydrogens, that they are provided by 6 molecules of hydrochloric acid. We have added 6 molecules of chlorine, that will leave as chloride ions. As the reductor used is tin, we can add 6 atoms of tin that will form 6 tin chlorides. In part E, of question 20, we are given the synthesis of 1-phenylethanol from 2-phenylethanol in 2 stages. We are provided with an schema of the 2 stages, and we are asked to suggest reagents, conditions, and equations for each stage in the synthesis, showing structures for organic compounds. The reaction is the transfer of the hydroxyl group, changing from a primary carbon to a secondary carbon. This can be achieved via formation of alkene followed by addition of O with steam. The stage 1 is the dehydration of the alcohol, performed with strong acids, such as sulfuric acid and heat. However, the marking scheme does not mention heat. In the stage 2, the alkene is then treated under steam with strong acid that will act as a catalyst. Following Martinikof's rule, the OH will be inserted primarily in the secondary carbon. In part F, of question 20, we have the statement that acid anhydrides react in a similar way to acyl chlorides with phenols. Benzoic anhydride is the acid anhydride of benzoic acid. Benzoic anhydride reacts with butan-2-OL to form an ester. We are asked to suggest an equation for this reaction, showing structures for organic compounds. We can use C6H5 for any phenyl groups. The acid anhydrides are formed from the dehydration of two carboxylic acids, and its formula is. The esterification reaction of an acid anhydride with an alcohol can be visualized as. The balanced equation of the reaction is. A valid alternative is to use 2-butan-2-OL and form two esters and water. The structure of the ester produces. In question 21, we are asked to describe the formation of carbon-carbon bonds in aliphatic compounds by two different mechanisms. Our answer should include mechanisms for each aliphatic compound. The most common ones are the addition of hydrogen cyanide to haloalkanes and to carbonyl groups, either aldehydes or ketones. There are more possible methods like the addition polymerization of alkenes or the radical substitution. However, this latest method does not allow good control of the products obtained. I will answer the question using the addition of hydrogen cyanide to haloalkanes and to carbonyl groups. The use of bullet points make it easier reading for marking. Substitution of halogenoalkanes with cyanide ions. The reaction is the replacement of an halogen, X, by a cyanide group. The conditions are potassium cyanide with ethanol and heated with the halogenoalkane. The mechanisms is nucleophilic substitution. As the halogen is more electronegative than carbon, the carbon-halogen bond is polarized and the carbon atom carries a partial positive charge as the electron pair in the carbon-halogen bond is drawn towards the halogen. This allows the attack of the nucleophile cyanide ion, Cn-, to the carbon. The lone part of electrons from the cyanide is used to form a carbon-carbon bond, and the halogen takes both electrons of the carbon-halogen bond. Nucleophilic addition of cyanide ions to carbonyl groups, aldehydes and ketones. The reaction is the addition of a cyanide group in a carbonyl group to form a secondary alcohol next to a nitrile. The conditions are aqueous solution of potassium cyanide and acid. The mechanism is nucleophilic addition. The carbonyl group becomes polarized because oxygen is highly electronegative. Electrons in the carbon-oxygen bond are pulled towards the oxygen atom, giving it a partial negative charge and leaving the carbon atom partially positive. This positive carbon atom is susceptible to nucleophilic attack by the cyanide ion, Cn-. The lone part of electrons from the cyanide is used to form a carbon-carbon bond, and one pair electrons in the double bond carbon-oxygen is transferred to the oxygen, leaving the oxygen with a negative charge and a lone part of electrons, that react with a proton forming a hydrogen-oxygen bond. And this is the end of the question paper. If you found this useful, please click like, and leave a comment, as it will help me to carry on making more videos like this.